Everyone, I hope you're doing okay. This is our last lesson of the Transformations of Functions unit, lesson 5. At the top here, this is from 2022. If this doesn't apply to the year you're in, then you can ignore it. But for those of you, we have our test on Monday, December 5th, and your Desmos assignments due December 9th. So this is our last lesson of the unit, and it's kind of a departure from the regular transformations that we were talking about, and it's a really specific case where you have what's called inverse of a function. And the inverse of a function is kind of like undoing something. Like if you take, tying your shoelaces, untying your shoelaces would be the undoing of it. It's the opposite of what's happening. We talk about inverse operations, like if I was to say the inverse operation of multiplication, the inverse operation of that would be division. The inverse of squaring would be square rooting. And so in math, there's a lot of cases where this is really important. Like if you were to go from, temperature degrees in Celsius, and then you wanted to convert them into Fahrenheit or vice versa, that would be kind of the inverse of it. The concept is not super complex, but the notation can be a bit confusing. But let's just start with the concept and then we'll look at the notation. So the inverse of a function has all the same points, except for what happens is the x's and the y's have been reversed. So for example, if you have a point x comma y, what happens is it becomes y comma x. And if that's the case and you have the inverse, we denote it like this. So we have, here's our regular function f at x. The notation of the inverse becomes f to the negative 1 of x. But what's really, really important is to note that this is just notation. It doesn't mean that this is an exponent. It just means that you're representing the inverse of something, in this case f of x. And we'll look at that and talk about it a bit more as we go through. So let's say at example 1 it says, let's say we have a function that is really just given by these points. And there are 3 points here, point 1, 0, next point negative 3, 5, and 0, 4. That would mean that the inverse of this, so the inverse of that function would be, you would have the point where you'd switch, so the x becomes 0 and the y becomes 1. And the next one, it would become 5 comma negative 3, and you kind of get the idea. That part is really relatively straightforward. You're just switching which ones are x and y, and that would be the inverse. What's interesting is, if you were to have the domain of the original function, those domain values now become the range and vice versa. And we'll look at that again later on. So let's take a look at an example here where we graph it. So let's say I've got this table of values, and this table of values represents f at x. This isn't any of our base functions. The points don't really work for that. But let's say I'm going to take those points, and let's plot them here first. So take a moment and plot them. I'm going to kind of do it a bit quicker. And for the purpose to see what happens, I'm going to connect these points. So that's f at x. So those are our original points. If I look at the inverse, so I would say the inverse then is f to the negative 1 of x. If I flip these, one of these points doesn't change at all. That point, 0, 0, is called an invariant point. An invariant point is one where even though you take the inverse, it doesn't change the point. So I'm just going to say down here, 0, 0 is an invariant point. And so the next one, if I switch that point, 2, 1 becomes 1, 2, and this one becomes 2, 5, and obviously this is 3, 10. So there is my inverse function. So if I graph that, there's that 0, 0, it didn't change. And then I have 1, comma 2, and you can plot these in, 2, 5, and 3, 10. Again, if I connect those, it looks like that. And I'll label this f to the negative 1 of x, or the inverse of x, of f of x. What's interesting is you get this kind of visual relationship where it kind of looks like things have rotated a little bit. And it happens that it is what's called a reflection, but it's a reflection over this line, and you can kind of dash this line in on your note. This is the line of y equals x, which is to say that that's a straight line where the slope is 1 and the y-intercept is 0. This is that line. So imagine you flipped the original function, and if I could show you with my hands, I would show it, but if you flip the original function over that thing, you get the green function. So if I was to describe this, I would say the inverse graph is a reflection over y equals x. That will always be the case for the inverse of a function. So if you graph something and it doesn't kind of look like that, like it's been flipped over that imaginary line, then you probably have some mistake somewhere. So let's take a look at one of our base functions and then see what the inverse of it looks like. So it says graph f at x equals x squared and its inverse. And obviously if it goes too fast here, you can kind of pause to catch up. So I'm going to put down my key points, which hopefully at this point you're starting to remember. And these are my key points for this specific base function x squared. So I've got these ones there. If I plot those, I've seen this many, many times, connect them, nice curve. There's f at x equals x squared. So I'll just label it f at x. So the inverse of this, so I'm going to take the inverse, I'm going to switch all of these. So again, that process is nice and easy. Now, I want you to graph it. Let me just fix this here. Graph it and see what you think about what it looks like. I'm going to graph that part and then graph this part separately like this and label it, of course. And again, you can see this has been flipped over my y equals x, like that. So if you look at just the top part here, so I'm going to highlight this briefly. Just look at the top part. Do you recognize that graph? And hopefully you do. And ding, ding, ding if you got it right. But this is just the root function, root x. So that square root of x is the top part. Now, if I look at the bottom part, this part down here, that looks also like root x, but what's happened is, and hopefully you recognize it, it is the reflection of that over the x-axis, which is the negative of root x. What's happened is the original function, which is x squared, the inverse of x squared is plus or minus the square root of x. And there's a reason, and we're going to show it algebraically, but let me just label this f to the negative 1 of x. The actual equation is plus or minus root x. If you think about x squared and the inverse function of that, the inverse function of squaring is just square root it. And so what happens is you get the inverse operation, and I'm going to show it algebraically below. So again, if you need to, you can pause there for a second. So graphing the inverse isn't so hard, but sometimes getting the inverse equation can be a bit challenging. And this is really the first time in this unit where we have some algebra involved. So let's say I want to show the inverse equation of this function x squared. So the first thing is to get rid of f at x and replace it with y. So I'm going to say y equals x squared. So I have it in terms of just y instead of f of x, which is totally allowed to do. And on the side here, I've got the steps once you get beyond that. It says the next thing to do is to switch the spots of x and y. So you switch them, but you keep everything in the original position otherwise. So in this case, there's just a squared. So that squared now becomes on the y. Technically, so this would be step one, technically this is the equation of the inverse, but in math we don't generally leave it as x equals y something. We generally rearrange it so it's y equals. So the second step is to isolate for y. So to isolate for y, I have to get y by itself. So right now it's y squared, so that means I need to take the square root. So if I do that, I get this. The only problem here is that I don't know if the square root is a positive square root or a negative. So this is how we get the positive or negative. We put it in front. So we always have to, unless we know it's not the negative or not the positive, we need to include it both. So what happens now is that cancels with my root. And so this is, I'm going to switch sides. Y equals plus or minus the square root of x. And that's the equation. Our last step is to just simply state that. So step 3 is to say, okay, rewrite this with the function notation. So f to the negative 1 of x is equal to plus or minus the square root of x, like that. So now one is pretty straightforward, a pretty simple example, but those steps will always be the same whenever you're trying to get the inverse function. So let's take a couple examples down below. It says state the equation of the inverse of each. If you want to, you can try this on your own, but I'm going to go through them. So first step, replace f of x with y. Second step, I'm going to switch x and y, the locations. So I get like this. Notice this one, I did have more things on the y side or on the x side, so those things stay and now they're associated with y. So beyond that, I'm generally just isolating for y. When I isolate for y, as a general rule, I would move over first the things that are easiest to move over. So right now I've got a negative 3, but I also have this multiplication of 5. The easiest thing to move would be the negative 3. So this is going to become x plus 3 equals 5y. And then the last thing I need to do is just divide by a 5 on both sides. So I end up with y, and I'm going to write as y equals x plus 3 over 5. And that is my inverse. So I would state that. So this is f to the negative 1 of x is equal to x plus 3 over 5. There's my inverse equation. Just so you kind of get a visual of this, if I graphed the original, it would kind of look like this. It's got a y-intercept of negative 3. That would be f of x. And then the inverse of this would be one that's much more shallow, like this, something like that. And so here, my original was a straight line, and my inverse will remain a straight line. It doesn't change, and that will always be the case as well. Sometimes nice to see all the connections. So if we go on to the next one, again, you could kind of try this one if you want. Y equals, and then I switch locations, so I've got x equals y squared. That's really the key step to not forget. Now I move things around, so I isolate for y. And when I get to this stage where I've got a y squared, I have to take the square root. So I've got plus or minus the square root of x minus 3, and that gets rid of the squared. So then I got y equals, and I can rearrange this. So I've got, this is g at x. So I'm going to now say g to the negative 1 of x is equal to plus or minus the square root of x minus 3. And that gives me the inverse equation. So those ones aren't so bad. They can get a bit trickier. You're going to see later on in the you try section, and I'll go through those with you, but it can get a bbit more complex algebraically. So let's try this question then, where it kind of brings together everything we've done in the unit into one equation, one question. It says, given h at x is equal to this, determine the equation of the inverse curve. So I want the equation of that. And then we're going to try to sketch both the original and the inverse, and we're going to try to state the domain and range. So a lot going on in this one. So the first thing, let's try to find the equation. So I'm going to rewrite this as y equals square root of all what we have there, like that. And first step, I'm going to switch these like that. Again, general rule, move across the easiest thing to move. So this is going to become x plus 1. And now we're at this kind of point where there really is only one thing we can do. This square root is keeping those 2's inside kind of like they're in jail. I can't do anything with them because of the square root. And so to get rid of the square root, the complement or the opposite function of square rooting is to square. So I'm going to square both things. So I'm going to square both sides of the equation. What happens with the right side is that square just cancels out the square root. So I now have x plus 1 bracket squared equals 2 bracket x minus 2. Now I can continue on in the same steps kind of as normal. So I'm going to get rid of this 2, which is multiplying, so I divide that. So that becomes over 2. So I'm going to have x plus 1 squared over 2. And then I'm just left with y minus 2 over here. And I can add that over, and I'm going to switch sides here. Like that. And that is, in fact, my inverse. So I've got h, the negative 1, equals bracket x plus 1 squared over 2 plus 2. And that's my inverse equation. So that takes care of that. Next step, we're going to try to graph this original h at x. So I've got this thing I'm going to try to graph. So first thing is to recognize what the base function is. And so hopefully you see that because I've got the root, this is going to be root x. So I'm going to take the key points for root x. Again, hopefully these are kind of, maybe not totally committed to memory, but make some sense. I pick perfect squares in order to sub in, and that gives me whole value answers here like that. So I'm going to take those, and then I'm going to do, remember, I want x over k plus d and ay plus c, that little algorithm that we use. So the x over k, first thing I need to do is recognize what is k here. So if I look at my equation, there's k. Do I have a d? Yep, I've got this negative 2, and then I also have this thing on the outside, which is the c. And so in this case, I'm going to have x over 2, and then because it's minus 2, I change it to plus 2. So that gives me my x values. In this one, there is no a, so I just have y and then minus 1. So that gives me my little algorithm to take my key points and transform them. So if I do that, I'm going to kind of go quick on this. 0 divided by 2 is 0 plus 2 gives me 2. If I take 1 divided by 2, that becomes 0.5 plus 2, that's 2.5. This one, 4 divided by 2 plus 2 is 4. 9 divided by 2 is 4.5, plus 2 is 6.5. So there's my x values. And then the y's are easy because I just subtract 1. That's negative 1, 0, 1, and 2. So let's sketch the transformed one. Again, you may have to kind of press pause to catch up, but that's okay. And 4, 1. Our last point here, 6.5, comma 2 goes off the graph, but I'm just going to kind of guesstimate where it is. So there is my original h at x. Oops. So that's h at x. Now, we also want to graph the inverse function. The problem here, and maybe hopefully you're thinking about this, the most efficient way to graph the inverse is to take my transform function and just switch x and y. So if I have this, so let's say I've got the inverse. I'm going to kind of try to squeeze this in here. Maybe I'll do this over to the side. So let's do it over here. I'm really just going to switch the x and y's for my transform. So this becomes negative 1, 0, 1, 2, and 2, 2.5, 4, and 6.5. So as long as I've graphed the original correctly, this is going to be perfect for my inverse. So if I graph these, there's that one, 1 and 4, and then the last point again will be off the graph, something like that. And there's my inverse. Great. And you can see it definitely looks like it's been flipped over that y equals x. So my last step in this case is to find domain and range, and this is really just to connect the ideas that domain and range have. In this one, my original one, the green one, if you look here, I've got x is all real numbers, but x starts at 2 and gets bigger, so I say it's greater than or equal to 2. And then my y is all real numbers, but my y starts at -1 and goes up. So I would say it's greater than or equal to -1. Now if I look at the inverse, so the inverse one, so these are my h to the -1 of x. This one, the domain is all real numbers, but it starts at -1, right? So there's my -1, so x is greater than or equal to -1. And if I look at my range, I've got y is all real numbers, but this one starts at +2. So I've got y is greater than or equal to +2. If you look at the domain and range of the original versus the new one, my inverse, they've switched. And that, again, will always be the case. My domain and range will switch between the two. Okay, that kind of takes care of those. Try the U-try. These ones are a bit tricky, so I'm going to there's a couple little tricky parts to them. I'm going to go through this, and I'm really just going to explain the tricky parts, so I'm going to kind of go quickly through this part. Try this yourself, though, so pause the video, see where you get. So at this stage, this is where it is a bit tricky, and I'm going to show you two different ways to do this. Ultimately, I need to get the y out of the denominator. So what I'm going to do is I'm going to multiply the y plus 1 to the other side. So I've got y plus 1 and x plus 2, and that's equal to 1. The problem with that is that I now have this x plus 2 times the y plus 1. So what I need to do is divide everything by that. So I end up with 1 over x plus 2. What's really happened is these have switched position. It's kind of like a cross multiplication. Now that I have it set up like that, this really becomes y equals 1 over x plus 2, and then I move the 1 over so it's minus. And that gives me g at x, or g to the -1 of x rather, is that. You could think of this another way, and I'm just going to put or here. This original x over 2 is really over 1. If I gave you this ratio, and this will always work in math. If I have this ratio, 2 over 3 is equal to 4 over 6. We know that's true. They're the same thing. They're equivalent. I could really think of this as, imagine I flipped both. 3 over 2 then should be equal to 6 over 4. If you have just those ratios set up like that, you can technically flip them. So imagine in this one, I've got x plus 2 over 1 equals 1 over y plus 1. There's no reason why I can't just flip this so it becomes 1 over x plus 2 equals y plus 1 over 1, like that. Similar idea to those numbers above. Now when I have it like that, that's much easier to work with, so I end up with y equals the same thing as the previous one, like that, and there's my inverse. Again, two ways to think of it, get the same answer. Okay, the last one here, again, I'm going to kind of jump through this a bit quicker. Try this yourself. Oops, don't want the color. So rearrange this. And at this stage, there's this negative. Before I take the square root, because I've got a squared, let me just fix that, I have to move the negative over. So the negative is like a -1. So you can think of it as you're dividing by -1. You can also think of it as multiplication by -1, but maybe division makes more sense. So this becomes x minus 3 over -1. That gets rid of it on the right side of the equation. Really, this is the same as -x plus 3. I'm dividing both of those terms by that negative, like that. That's the tricky part in this one. Now what I need to do is take the square root, and I'm kind of running out of space here. Let me just move this over a little bit. You have to remember to put the plus or minus. It's so easy to forget it, but really I'm taking the plus or minus, and that gets rid of this squared with the square root. So I now have y minus 2 equals plus or minus square root of negative x plus 3. And I move the plus 2 over. Like that. And there's my inverse equation for this function. So this is k to the negative 1 of x equals plus or minus what we have written. Great. So try those ones, and here are some good practice questions in the homework. Otherwise, if you have any questions, let me know, and I will see you in class. Take care.